Dr. Schoffer speaking here. Moving on in chapter 17 that is concerned with aromatic compounds. So this part of the video lectures will focus mostly on the unique stability, as I'd mentioned before, of benzenes of aromatic compounds. But let's focus on benzene itself. One thing I regret in how a lot of these topics are covered, it's sort of like revealed wisdom. Here's what you need to know, learn it, practice it. But there's a real history as to how scientists pursue truth-seeking, like what is going on in nature, how can we explain phenomena. For chemists, that the focus is very much on reactivity of aromatic compounds. One thing we want to definitely understand is that these aromatic compounds have unique, remarkable stability. If we draw parallels to everything you learned in the alkenes chapter, especially electrophilic addition reactions, here is a cyclohexene and a reaction with Br2, and it would go via a bromonium ion intermediate. Remember that 3-member cyclic component, and then you would get trans dibromide plus the enantiomer. When we are looking at an aromatic ring like benzene here, and we use the same reaction conditions, we get no reaction. So that tells us that even though we see a double line here to represent the double bond, this double bond is very, very different from this double bond. And we'll learn in the next chapter, but I'll try to draw it right here. I'm going to copy benzene over. I'm going to write a reaction arrow. And now I will use, again, Br2. Okay, and if there is a catalyst in here, so that's what the next chapter is mostly concerned with, such as FeBr3 would be one, there are many other ones, or AlBr3, you will get a reaction. And I'm going to put an exclamation point here. And in fact, what you will get, I just want to highlight this already so you know where we're going and why we're learning so much about aromatic compounds before we talk about reactions. So this will then actually turn into a substitution reaction. So I'm going to abbreviate the aromatic ring with phenyl. And now I draw one bond to bromine. And we will study the mechanisms in detail, which means you need to do well with your curved arrow formalism, formal charge calculation, understand where the electrons go. So basically here we get a substitution reaction, and that is very different from the reactions we see for the alkene. Here we have an addition reaction. So we can abbreviate that to DDN. Okay. So we'll look at the reactivity in chapter 18. First, we have to understand why that unique stability. But bottom line is, this double bond is different from this double bond. And one of the reasons why I had you actually start out the chapter by drawing a cyclohexane, cyclohexene, cyclohexadiene, and then a cyclohexatriene is because when we are looking at stability, we need to understand heat of hydrogenation, and that's on the next slide. Here we see delta H naught determined for 4 scenarios. Cyclohexene is not in here. Cyclohexene is the product if you were to reduce all the way down all of these compounds. So 1 mole of hydrogen would get you to a cyclohexane. You can also draw it just flat, but we do know that there are conformations and ring flips. This will become more important again when we look at derivatives and carbohydrates many chapters down the road. But here we have hydrogen being added across each double bond. In this case, it's just 1 mole. Then you get cyclohexane. We can measure the energy that is being released. The higher the molecule, the less stable. All right, so when we go from cyclohexane and we have a double bond, that makes it more reactive. That's why it's less stable and higher in energy. If we introduce 2 double bonds, here we could then add 2 hydrogen molecules to then result in cyclohexane. We see that this is even less stable because we now have a second double bond here. And then when we add a third double bond, this is what would be expected, right? If we say that per double bond, it costs us about 120 kilojoules per mole, and that times 2 is about 240. Okay, so it's a little bit less. And of course, we learned about the stability of a conjugated system, but still it's high in energy. So we would then expect 3 times 120, so that would give us 360. And yet what we find is that benzene is actually more stable than the diene. Okay, and when I said draw cyclohexatriene, that's this one. It would mean that there's no communication between the double bonds, that conjugation would actually not be possible. That's how we dealt with this and came up with the expected number there. Lo and behold, an aromatic compound, when we hydrogenate it, add 3 moles of hydrogen to make cyclohexane, we only get 208. And we also talk about the difference here as the stability, the unique stability that ensues from having these double, single, double, single, double, single bonds in a cyclic array. We have 6 electrons, and that is going to play a really important role. We're going to go back to some more sophisticated blobs. Here you see some illustrations as to molecular orbital description. So MO theory we covered extensively in chapter 16. Remember that we have here, I'm just going to copy this over. We have these molecular orbitals. I would like to simplify this a little bit. Benzene has 6 carbons, 6 atomic orbitals, or 6 atomic p orbitals will give you 6 molecular orbitals. Here they are. The lowest energy one is the simplest one, and that is where there are no nodes. So we have the colors lined up all around, and that makes it the most stable one. Since we are dealing with 6 atomic p orbitals, we have 2, 4, 6 electrons in here. So you can fill these in. I won't do that. That's also what's shown here. And you can also look this up in the textbook. The other important thing to recognize is that there's a symmetry here. Remember that this is the non-bonding level. This is where the energy level is for p orbitals that are not having any interactions with each other. They're isolated p orbitals. Then they come together. And as you go up in energy, the number of nodes increases. You see that there's a degenerate level here, a degenerate level here, and then the highest level here. We are able to fill all 6 electrons all in the bonding molecular orbital energy category. And all of these are the anti-bonding ones. So those would be your star levels. The other thing I'd like to point out and give you a little step ahead is that we can actually predict the levels of these molecular orbitals. And there's a very nice mnemonic, a tool to remember where to place the levels. This is very different from our polyenes. We now deal with cyclic structures. And the shape of the molecule plays an important role here. Step 1 is draw a circle. So you start to draw a circle. You inscribe a polygon, making sure that one of the connecting points is at the bottom of the circle. So you see how this one here, this is the 7-membered ring. This is pointing down. But wherever you then have a band, a carbon placed, that will be the position of your energy level. Well, when we do this here, all we need to do is draw our benzene, our 6 carbons. You can draw the circle first. Sorry, this is a bit crooked. But now you see these are the levels, and we can, from the shape of the molecule, and we want to have this carbon needs to be down here. So doing this kind of, oh, this is bad. Let me just erase this real quick. I'm going to try a little harder. If we were to rotate this, and have the six-membered ring oriented like this, it would be a 2-2-2 level. That's energetically actually not favored and is incorrect. Okay, so you need to have this pointing down. So this will predict you the relative MO energy levels, and I wanted to integrate this as I'm going through some of these first examples. Next slide shows us that there are certain rules that will help us understand why benzene has a unique stability, but cyclobutadiene does not. Okay. There is something known as the Huckel's rule using the MO theory. For benzene, we have 6 electrons, so that's here. And for butadiene, we have 4 pi electrons. When we fill in these energy levels, and I'm going to try to attempt this here on the side. So we had our benzene energy levels. So we had determined this on the previous slide. I have to fill in electrons. And why is it that this will be called aromatic, but this will not be called aromatic? So we want to reason and deduce what is going on. Remember how I said this is the non-bonding level? Then you have the bonding below and the anti-bonding above. Okay. When we draw the plane of symmetry here, again, we show the bonding molecular orbitals. These 3 here are below that non-bonding level, and then we have the anti-bonding ones, but there are no electrons in here. So when we lack a closed shell electron configuration, it becomes unstable. And in fact, because we have a 4-electron system here, and a 6-electron system here. This now comports with what is required for aromaticity, which is 4n plus 2. We're going to get to that. And here we have a 4n system. Why is this important? Well, look at this. We have 4 electrons in the system. 2, 4. We fill the lowest one, and then we have to fill 1 into each separately. And this is at the non-bonding level, which means that this is far less stable, and that's why it's called anti-aromatic. Anti-aromatic, 4 electrons, which will comport with the 4n rule, while 6 electrons will comport with the 4n plus 2 electron level. So here it is summarized. Aromatic compounds must meet 2 criteria: a fully conjugated ring with overlapping p orbitals. That means they need to have the geometry so that they all align. So we had seen this with, let's say, butadiene, right? So we see the similarities, but we also now need to understand that this overlap is only possible when this is planar. Overlapping p orbitals means it must be planar. All right. Now, it also needs to meet Huckel rule, an odd number of electron pairs, which would mean 6 electrons. It could also mean 2 electrons. And the formula that becomes helpful is the 4n plus 2 total pi electron system. If n equals 0, we get 2 electrons. And there is, in fact, such a scenario that's covered at the end. If n equals 1, you get 6 electrons. So you just plug into that formula. So these are the requirements for the number of electrons necessary for a molecule to be aromatic. Now, the following two compounds do not meet Huckel's rule because these are 4n. We have 4 and 8 electrons, and you can practice this with the conceptual checkpoint. All right, there's more information in this section, 17.4. I decided on the next slide to jump ahead a little bit and put it in context. So here's just one slide from 17.5, because we're going to have a broader definition as to what it takes for a compound to be aromatic. In fact, not just aromatic. So we have aromatic here. We're going to differentiate to anti-aromatic and non-aromatic. Fully conjugated system with overlapping p orbitals, which means it has to be planar. Meets the Huckel rule, 4n plus 2, so 2, 6, 10, 14, 18 have the potential to be aromatic, but they need to be planar. So we go in steps of 4. We start with 2, plus 4 is 6, plus 4 is 10, plus 4 is 14, plus 4 is 16. Anti-aromatic are all those compounds where you have fully conjugated ring with overlapping p orbitals, which requires it to be planar, and an even number. So now we're talking about 4n. That would be 4, 8, 12, so on and so forth. Very often, anti-aromatic compounds will try to not overlap and twist themselves out of this because it is actually energetically more favorable to be non-aromatic, which means they miss the planarity of the molecule, which is in opposition to the aromatic and anti-aromatic requirement. Let's go back to section 4, stability of benzene. Here we have this a little bit more expanded. Remember that the lowest molecular orbital will be the one where all the colors are aligned, whether it's red and blue on the bottom or shaded on top and not shaded on the bottom. Again, understand where the non-bonding electrons are. Molecular, this is the non-bonding p orbitals, and then we have 3 bonding and 3 anti-bonding, and we're only populating the bonding molecular orbitals, which yields with that unique stability. There are sophisticated high-level mathematical calculations. We can still apply some of the symmetry functions we've seen here, but most importantly, understand where the energy levels are and where you place the electrons for each system. The delocalization of the 6 pi electrons in the 3 bonding molecular orbital accounts for the unique stability that we had seen with the heats of hydrogenation. Stability of benzene. Not all fully conjugated rings have aromatic stability. Again, here is your 4 electron system, which is 4n. Here you have your 8 electron system, which is also your 4n formula. So some fully conjugated cyclic compounds react like normal alkenes because this is actually, when you look at the shape and you have pictures of this is not planar. It has to avoid some of the distorted bond angles. It goes into a tub kind of arrangement. And here's an example how you can actually make, using some pericyclic reactions, how you can get to this compound. But let's focus on the next aspect. So as we run through this, same thing we did with aromatic, benzene. So aromatic compounds have to get the 4n plus 2, but here the Huckel rule is not met, because it's a 4n system, as I said before. Here again, I want to highlight how we can use the molecular shape to anticipate this, the placement of all the molecular orbitals. I really want to do this one more time, because you will have to be able to do this with other systems as well, and understand how many electrons go in there. So if you would have to find where the non-bonding level is, you will take the shape of the structure, you're going to have to basically have drop down, straight down to this level here that you can then see. And because we now have, this is also referred to as an open shell configuration. Open shell, which means these are not enriched. Now, if I was to actually pump 2 electrons into the system, I could change the population of electrons. But we're lacking a closed shell. This is an open shell because of the lack of a pairing electron, and therefore it's unstable and it's anti-aromatic. Similarly, as we look at this again, we can, oops, let me jump back again. We can place this and see how you have to actually have one of the vortex point down to the lowest level. So when you connect, you see the shape of this 8-membered ring. It would actually go in a little bit like this. I'm not doing a very good job with this, but you have some prettier pictures in the book. So you have to align the cyclic component, and these would be the levels that you get, and then you can place 2 here, 2 here, 2 here, and again we have this open shell situation, 2 molecular orbitals on the non-bonding energy level. That's a disadvantage, therefore it's anti-aromatic. And in order to avoid that very unfavorable energetic situation, the molecule will try to avoid this by twisting into a tub-shaped conformation. You now see that these pi orbitals are not overlapping. It's energetically more favorable. So we don't have the conjugation all around the entire ring. And so instead of this being anti-aromatic, it assumes this arrangement to be non-aromatic, which is low in energy. And on the next slide, we have the summary of the frost circle. So we had just seen this. We predict the shapes and energies of molecular orbitals to simplify and predict the relative MO energies. And I would probably say energy levels, right? So we want to have this in context of here. This is the important component. This is our energy axis. Yeah. And then we have to place all the levels. So we had seen this. Be able to reconstruct this. Draw your non-bonding level. Differentiate between bonding and anti-bonding, and on you go. On the next slide, you have the summary for many of these. So it helps to explain why the 4n+2 rule is so critical. 4n+2 means that we only have an odd number of bonding MOs. There are 3 here. There are 3 here. There are 3 here. There are 3 here. So work your way through here. Pause or reread it in the textbook. Take copious notes, and then also practice with conceptual checkpoint. Note that the number of bonding orbitals is always an odd number. Yeah, and this frost circle will help you place the energy levels and then think about how many electrons you would place in here. Well, again, the 6 electrons, really, really important for the stability. We'll take a break here.